not go to torch, we'll stick to the SI units. Yeah, so it's not at 1 atmosphere. So let's say we are sitting somewhere over there. We have the liquid at 1 atmosphere or whatever. So I now close the system. Right? I put it in a sealed container, a strong sealed container. And then I start heating it. What would happen? Some of the liquid will turn into vapor. Right? And depending on the temperature, and let's say the vapor is now saturated, I cannot have more vapor. That temperature would give me a pressure which would lie on this particular line. Yes, the liquid vapor curve. So now I keep on heating it. So I'll do it very slowly. Yeah, I slowly keep on heating it. So the pressure of the vapor cannot be anything else, but it has to lie on this particular line because the volume is fixed. So I have absolutely that amount of volume, and whatever the vapor comes, it saturates. We cannot have more vapor than that, right? So it keeps on accumulating. Now, what is happening? When more and more vapor is coming in the same volume, the density of the vapor keeps on increasing. At a certain point, the density of the vapor becomes equal to the density of the liquid. Once that happens, you cannot distinguish between the two. And in an experiment, if you do it, you'll actually see the meniscus vanishing away. So you will not see that liquid vapor boundary. Now, so that kind of a phase diagram. And you just already saw that if I change the temperature in this closed vessel, my pressure is governed by this particular line, the liquid vapor line, right? It's always in equilibrium, right? It's in this closed container. The liquid and vapor are always in equilibrium. There can't be anything else. So I can also vary my temperature at will. I cannot vary the pressure at will. So my pressure gets fixed. It gets not exactly fixed in the sense that you have only one value, but it gets dependent on the temperature that I have. Right? In other words, I would say that I have only 1 degree of freedom, and that is either temperature or pressure. I could vary temperature, pressure would follow. I vary pressure, temperature would follow. I would always stay on that particular curve. So I have only 1 degree of freedom over there. So degree of freedom. Defined by or denoted by S. If you think about any of those lines, the solid vapor line or the solid liquid equilibrium, everywhere we have only 1 degree of freedom. Right? I vary temperature, the pressure is defined, so it cannot be anything else. You'll have to stick to this curve if I am at equilibrium, right? Now, what about the rest of the things? Take the rest of this phase space. Over here, I can vary my temperature at will, and I can also vary my pressure at will. For one temperature, I could go to any pressure. Right? So both are independent. In this space, in that space, over there, everything is independent. So my degrees of freedom are 2. Right? And if I think of this particular point, the triple point, my temperature is, for example, for water, is 273.16. The pressure is 611 millibar. Right? 10,000 millibar. No. 1,000 millibar is 1 atmosphere, right? I hope the number is correct. Anyway. Now, No. The thing is that these two, both temperature and pressure, they are both fixed. I cannot change anything for the triple point. If I change anything, I will not be at the triple point. Which means my degrees of freedom now are 0. Okay. So, it really depends on where you are, right? So, if I look at any of the region in the phase space that does not lie on the line or the point, then I have to worry about only one chemical potential. The chemical potential of the gas, right? So there's nothing governing it. You can have that chemical potential. Any chemical potential doesn't matter. If I think of the line, then what I have to worry about, since I am at equilibrium, and just now we defined something that at equilibrium the chemical potentials of the component in all the phases are exactly same. So now we have two phases at equilibrium. So let's say either the liquid phase and the gas phase, or phase alpha and phase beta to be more general. So mu of phase alpha at pressure and temperature should be equal to mu of phase beta at pressure and temperature, right? At the same pressure and temperature. What does that say? It says that, look, I'll get one equation, right? I have to solve for that. And if I have one equation and I have two variables, then one of them gets dependent on the other one. Right? If I use one fact like that, I get one equation, right? So and that's why I have 1 degree of freedom. Right? One is the dependent variable, one is the independent variable. I can change one at will. If I think of the triple point, there the chemical potential of all these three should be the same. So let's say mu of solid should be equal to mu of liquid, should be equal to mu of vapor. That gives me two equations, right? And I have two unknowns. So it just gives me 0 degrees of freedom. So there's actually a very general formula for finding out the value of F, and for any number of components for that matter. And let me evaluate that. Okay, so now let's think of so this is a single component what we just now saw. You could have either 0, 1 or 2 degrees. Yes? You cannot have 3 degrees of freedom. Huh? We have only 2 variables. So we can never have 3 degrees of freedom, right? So which means that four lines cannot come and intersect at the same point in the phase diagram. So we cannot have something like this. Because at the most we have 2 variables, right? And that's the maximum we can have. The third, if I get a third equation, it will be dependent on one of those 2 equations, or it will be a parallel. So that doesn't make sense. 4 of them cannot intersect. So the number of degrees of freedom, or 4 phases cannot coexist in a single component system, so as to say. Now, let's think of a multi-component system, right? And what all can I change in this multi-component system? Of course, the pressure and temperature I can always change. Right, so pressure and temperature I can always change. What else? I have a multi-component system, which is going from one phase to the other phase, to a third phase, to a fourth phase, I don't know, multi-phases also. We don't need to spell out the number of phases at this moment. So, I have this multi-component system, and just now I gave you an example of water hexane. A closed container water hexane, liquid, water hexane in the gas. Now, from common sense, what do you tell me? Do I have more hexane in the gas, or more percentage of hexane in the gas, or more percentage of hexane in the liquid? In the gas, right? So which means that I could even define that percentage as something like mole fraction. So the mole fraction of each and every component need not remain the same throughout all phases. So other than pressure and temperature, what I can also change is the mole fraction. So in order to define the components, I need to define all their mole fractions. So I need to define x1, x2, up to whatever x. If I have n components, or if I have c components, let's say c. No. What am I doing? Yeah. So if I have c components, I need not define all the c mole fractions, because all of them sum up to 1. So I need to define for c minus 1. Right? And I need to define these mole fractions for each and every phase that is present. Yes? So which means I need to define c minus 1 mole fractions for p phases. So p is the number of phases, and that p, I'll just make it small pressure, number of phases, and this is the number of components present. So what I have is that the total number of variables that I have now is p into c minus 1 plus 2. Can I vary all of them independently? Yes, no, maybe.